Hi everyone. So yeah, as you can see, I'm Victor. I work at INRA in Paris. I work for Julia and Jean-Pierre, who's not here today. So this is a list of people we work with, but today's presentation will be a bit different. I'm not going to talk about the kernel itself, but how we can use the kernel to help neutral exclusion in user space. So basically, we'll compare two different solutions, FlexGuard and the time-fast extension, and see how they help the user space locks and whether they do it well or not. So first of all, a little bit of background so that everyone is up to speed. So this is the state of the user space locking right now. Basically, the most common user space locks are basically blocking locks. They're used, for example, by the P3 mutex locks. So I guess most people know this, but these locks work this way. Let's imagine we have two different threads, and they each want to access the lock. If the lock is already taken by one thread, then the other thread will just have to wait for the lock, but it will do that using a mutex syscall, for example. It will block. And then once the lock holder releases the lock, it will wake up using a mutex wake syscall to wake up the next waiter. And the issue here is that the next waiter will actually waste some time because it will hold the lock, but it will not be running because there will be some context switch time. Basically, it's time spent between the critical sections. Now, the critical path looks something like this, where the critical sections are not one after the other. You have some time in between them. That is some wasted time. Now there is another kind of lock, which are spin locks. You probably know these. This is a very simple test and set lock on the right here. But basically, these locks are way faster, and that's why they are the most common ones in the kernel. So once again, the waiter thread will have to.
Needs to be a store release, otherwise it's broken.
Yeah. That's a very simple. Yeah, nobody uses actually this
pseudocode.
Yeah. There's no void or anything. It's like it's pretty good. So here, instead of blocking, the waiters will spin, so they will busy wait. You can see here it's just a simple spin loop. And in that case, the transitions between different critical sections will be much faster, and you can think that the critical path will look something like this, where each critical section will be right after one another with no wasted time in the middle. So now, why does no one use spin locks in user space? For example, as I mentioned, the P3 mutex locks from the glibc don't really use spin locks.
Well, people do use user space spin locks quite a lot.
Yeah, database people.
Yeah. Okay.
Game people do. Everybody does. And then they complain.
I don't think I use.
That's why we want the extended time slice.
It's there.
Yeah, they use some adaptive. I guess they use some adaptive spinning in not like unbounded spin locks. So now the issue is that spin locks performance collapses on oversubscription. So you can see on the right hand side you have the subscription on the x-axis, so it's the number of threads over the number of CPUs, and then on the y-axis you have the lock latency. So here we want to have the lowest latency possible. We compare a pure blocking lock to an MCS lock, which is a quite good spin lock, and you can see that in non-oversubscription, so when we have less threads than cores on the machine, the spin locks actually perform great, and it's not really visible, but here the speed up is 5 times. But the issue comes when you have more threads than cores on the machine. Then at that point, the spin lock collapses, and it's actually not even usable anymore because you can see that it's several orders of magnitude slower than the blocking lock. Now, the reason is that spinners, or basically any other thread on the machine, can preempt the critical section, which stops all progress on the critical path. Once again, I can show you this. So if we have only two CPUs on our machine and we have 3 threads, one of the threads can hold the lock, and then it can get preempted in the middle by a spinner or any other thread, basically. But the worst can be when it's a spinner that spins on the same lock, because as you can see, there's a whole time slice here, which is spent doing basically nothing. And then, the critical path will look something like this, where the critical sections are interrupted in the middle by spinning time or some other tasks. Now, can we solve this issue by just not having oversubscription? The issue is, I have some examples, but basically, for example, LevelDB, which we will evaluate later, is used by Chromium. And so in Chrome, for example, if you have too many tabs or too many applications on your machine, you could have some issue. This is just a simple example, but this is also very common in production. For example, Meta has a benchmark, which is called DCPerf, which kind of replicates the workload, the CPU workloads that they have in their own data centers. And in most of them, most of these benchmarks, they have more threads than cores. So this happens in practice. And finally, even if you have a very, your application is tailored exactly to your machine, you have exactly the number of threads that you need, then you can have other applications running on your machine, like monitoring, backup tasks, I don't know, any other things that can add threads and preempt the critical sections, for example. So oversubscription is an unavoidable problem. And so we can wonder whether spin locks can be fixed for user space. So there have been many different attempts at solving this, mostly by combining both, so spinning and blocking, to get the best of both worlds. But they all use unreliable heuristics, and most of the most complex ones are not really used in production. So the most simple one, and this one is very widely used, is spin and park lock. Basically, you just spin for some time before you switch to blocking. You have a heuristic, which is how long do you spin for, but yeah, most of the time we set the spinning phase exactly to the time it takes to have a context switch. But still, it leaves a lot of performance on the table because spin locks are most of the time faster than these locks. These are all just examples that you can think from the top of your head, but this is Malthusian locks, for example. It's just solution where you have different lists, and some threads do spin, some threads do block, and so you have less spinners, and you can hopefully get less preemptions. But once again, you have some issues, which is how long do you spin for, and what's the size of each list, etc. And that doesn't work very well on different machines and on different applications. You can also detect preemptions using a timestamp. For example, you store a timestamp whenever the lock is acquired, and then if the timestamp is stale, a waiter can guess that there's a preemption, and it can switch to a blocking lock. Once again, you have another heuristic here, which is what's the timeout. It will depend on the critical section, the application, etc., etc. And finally, this would be the most reliable approach, maybe, but this is another solution where you only acquire the lock if you have enough time left in the time slice. So this is done, for example, for Xen because the time slice is fixed in that case. But that doesn't work once again because how much is enough time? It really depends on the critical section and everything else. So now, how can the kernel support user space spin locks to work more reliably and work everywhere if possible? So I will present two solutions. So a first solution is a reactive solution. So it's a bit like the previous solutions I presented. This solution will detect the critical section preemption and it will switch to a blocking lock. So basically, it's once again a combination of both the locks, a spin lock and a blocking lock. So this solution is called FlexGuard. And then the second solution is the preventive solution where you preempt the scheduler from preempting the lock holder altogether. So there will be no preemption, hopefully, in that case. And this is a time slice extension patch that has been merged in, version 7 is not out yet, but it will be released next week, I guess. And time slice extension will be
yesterday.
Oh, yes. Okay, yeah, probably yesterday. So then it's live now. You can use that if you want. And we will we'll explain how it works and how it behaves.
Sunday.
So let's talk about the first solution, so FlexGuard. So in that case, the idea is to detect the critical section preemption and switch to a blocking lock at that point, and only switch to a blocking lock when there's a preemption. So basically, our target lock would be this line here, where we always perform as good as the base lock. So we can do this using eBPF without changing too many things. In the kernel, we could also implement the support in the kernel itself. But the idea here is to accurately detect critical section preemptions and then switch to block. So the way we do this is by having a preemption monitor, which detects critical section preemptions. The idea is to have a global counter of preempted critical sections. So we call it number of preempted critical sections. Basically, it counts the number of critical sections that are preempted on the whole process. And then there's a BPF handler that hooks to the scale switch event, and you can just detect and increase that counter or decrease it whenever needed. So how do you detect? Because with a BPF handler, we can detect when a thread gets preempted, but how do we know that that thread was actually holding a lock and whether we should increment the counter or not? So here is a very simple test and set lock. The first idea to detect whether a thread is holding a lock is just to store a flag somewhere. You can maybe add a flag, a per thread flag at the end of the lock function, and maybe remove that flag at the beginning of the unlock function. So here it's done using counter because you need to account for lock nesting.
But this is racing.
Mm-hmm.
It has a race window.
Yeah, sure, yeah. So that's why I'm gonna add more afterwards. But is that enough to be accurate? Yeah, no. The issue is it's not, the counter is not enough because, as Peter said, the critical sections actually start in the lock and in the unlock functions. So this is just a simple overview. But you can see that between lines 9 and 12, the thread can be preempted and it won't be detected by the monitor as a critical section preemption because the counter is not incremented yet. So for that, we can store some labels and we store them in a BPF map, and then the BPF handler can just look at that map and know that if the preemption happened around that label, between the label and the end of the lock function, basically, we know that we are in a critical section. There is still one last problematic case, which is that the preemption right after the exchange actually determine can be in a critical section or not, because the return value of the exchange actually determines whether the lock is held or not. And so for that case, we can store the exchange result in another register somewhere, and the BPF handler will look at the dumped register when there's a preemption.
Why don't you just store the task ID in the lock?
Yeah, that would be your solution, but then in that case, you need to have a global, you can do that actually if you use a test and set lock like this lock here.
I'm saying so the BPF program would just say, is this thread been preempted? So every time you have to know what threads are being preempted and what threads are not being preempted. So I guess
then you need the address of the lock value.
Yeah, also.
Wait, what? So if you just want to see but you just have to know what the task was. So when you, who runs the BPF program? The one that's blocking on the
one that is preempted.
Oh, wait. Oh, the one that's preempted runs the. Oh,
yeah.
I wasn't sure if you could add a BPF callback to when you acquire a lock. If it's blocked, ask the BPF program.
No.
You'd have to place.
That's right. So
new probes.
But the BPF program would have a map. So you just.
Horrific.
But doesn't BPF programs have like a map that user space could read?
So all of this assumes that user space is annotated.
Yeah, but not all of user space. Yeah, this can seem very complex, but this, like, only the log primitives themselves need to be annotated. The rest of the user space application does not need to.
Well, you want to cover your entire critical section.
Mm-hmm.
And this will be in the log user, not in the.
Yeah, but the flag will help to detect whether there's a critical section.
The race condition.
There's a preemption. Yeah.
Oh, okay.
Yeah. In the end, when we implement all that, we don't need to change anything in the application. In the end.
Well, only if they use the library.
Yeah, sure. Yeah.
Do you even need to detect with 100% accuracy?
Yeah, that's my next slide. So is it really important to be fully accurate? Actually, yes, we tested that, and it does need to be accurate because the critical section is often only a few instructions long, and so there's a high chance that your preemption will happen in the lock and unlock functions instead of just being in the user application. yeah, so if you don't do all of that, you actually still have a performance collapse compared to a blocking lock. Okay, and then so that's the way we detect preemptions, and with that you can create a lock. So basically, yeah, I'm not going to explain everything about this lock, but we use an MCS lock, which is a pretty good lock, and we use a global lock word. So for those familiar, this can be a bit similar to a Q-spin lock, where the very first spinner will spin on the global lock word instead of spinning on its own Q node. And that helps because we will switch to the blocking mode using that.
Yeah, saves the whole cache line dereference.
Yeah, also. So this lock works in two different modes. So in spinning mode, so whenever there's no preemption, the waiters enter the MCS queue just like they normally would, and then the first spinner spins on the lock word instead of its node. And then when a preemption is detected, all of the waiters will bypass the MCS queue and they will just use the global lock word as a futex word. And that means that we have a very cheap way to switch between a blocking lock and a spinning lock. And that is all done correctly. Like there's no issue from mutual exclusion. So now let me present the other solution, which is the preventive solution, the time series extension that has been released yesterday.
Another solution, I would say, because they are kind of they work together. They're mutually.
Yeah, that's the conclusion at the end. So the idea here is to prevent the scheduler from preempting the lock holder. So here is a very simple way. So it works using RSEC. There's a structure in the RSEC structure that allows the user space code to communicate with the kernel. So basically, you can request an extension. It's a simple write. You write one into this request field. And then you can execute your critical section. There's no lock here. So you execute something you don't want to be preempted. And then at the end of this something you don't want to be preempted, you can abort the extension. So just by setting this value to 0. But there's one more thing you need to do is if the extension was granted, you need actually to yield so that other tasks can run on the CPU. And this is, as I said, this is very cheap because this only writes and you have no synchronization or anything. These bits are set, are thread local bits, so you don't need to synchronize with other threads. So now the way we use this time series extension in a local algorithm would be by not requesting the extension when you spin, because I guess this is obvious, but this would be very bad to spin while you request the extension, because all of the spinners would then request the extension, and that would make us go back to square one, have the same issue.
You need to request it first, then attempt, and then clear again.
Yeah.
And then request.
Yeah.
Yeah. Well, yeah. I think that's where you get the queue. Well, the queue thing, right?
Yeah.
You only have, isn't it like only have one spinner?
Yeah.
Is it?
Exactly. So basically, we want to request the extension that, as you said, right before the log acquisition. So here I'm just showing an example using a simple test and set log, but we can use it with other solutions afterwards. So basically, we have a try log, a log that uses a try log to be acquired. We request the extension first, then we try to acquire the lock. If we succeed, we just return and we are still extended. But if we fail the acquisition, then we abort the request by yielding if necessary, etc. Just doing the same thing as I said previously. And then we can try to acquire this lock again and again, but only if the lock is free. Basically, we spin and we check the lock word first so that we don't request extensions too many times.
You need a compiler barrier in that while.
Yeah, sure, yeah.
Otherwise it can lift the lock.
Yes, there are compiler barriers everywhere. I did not show that. Yeah, at the beginning they were added, but it was it was longer. So.
Sorry, I've been looking at stuff too much.
Yeah. And basically, when you unlock, you can just abort the request once again and yield if necessary. But yes, the best solution to use the time series extension would be by supporting Q logs, which are better because there is less cache line contention, because each of the threads would spin on its own Q node and not spin on a global lock word. So once again, we can request the extension when a thread is the very first waiter. So we use the same construction as we did for the FlexGuard solution, where we use an MCS lock and a global lock word for the first waiter. So basically, we have this lock function. We first try to acquire the MCS lock, and then from line 3 onward, only one single thread can enter that path, and not other threads. So then the first waiter will request the extension, and it will then spin on the global lock word. Once again, there are compiler barriers here, but they are not shown. And then once you've got the global lock word, you can release the MCS lock, and so that the next waiter can try to get the extension and get the task lock. And then for the unlock, it's very simple. You just release the test and set lock and abort the request and yield if necessary.
Wait. So you're spinning while you have the request set?
Yeah. The spinning is actually, with the requested extension, is actually bounded to at most one critical section duration, because you will only spin on the test and set lock while you are the very first waiter. So the next one, the thread in front of you will be in its critical section, and you will wait for it to end its critical section, but you probably requested the extension while it was in the beginning of its critical section, and so you can only have at most one critical section long of a request while spinning.
But so, because this has the algorithm to go or check to see if the task is running. I mean, from your previous solution. So with both solutions, so this will only spin if the other task is spinning as well, or is in the critical section. Because if it's sleeping, if you preempt, so basically I'm saying without the previous solution, if this guy were to preempt the owner critical section, it actually just extended the critical section. So basically, if it preempted the owner, and it's saying, "Oh, don't preempt me, give me an extension," you just now extended the length.
Yeah, but basically here the owner will also be extended, so it should not get preempted. It can in practice, but the issue and why we need to do that is, and that's what I said here, is that if we don't do that, the time slice extension locks used with Q locks don't work very well, because there will be preemptions of the next waiter. Basically, the lock holder will be running, but it will give the lock to the next waiter, and that next waiter will not be running. And so you will pay the cost of a preemption at that point.
I see what you're saying. So it's at most 2x the section you're saying.
Yeah.
Okay.
But if you are relying on the separate CPU handling the different tasks,
yes,
it may have a live lock. If this one is requesting the CPU resource spin on it, and the other one, for example, the priority is not that higher and still runnable, for example, other real-time task on that CPU, I think, the system.
Spin locks user-space spin locks don't work for RT tasks.
Yeah,
you don't. That's when if you're going to use RT tasks, don't use user-space spin locks, because you could easily live lock your system.
Live lock. I mean, the system actually will have multiple tasks. Some real tasks may still live in that system, and the owner which own the current pthread mutex is a normal task.
Yeah, basically here we're making the assumption that all of the threads have the same priority.
Oh.
Yeah. So this is
have a big problem.
Yeah.
That's a priority convention. So different priority tasks may have the same mutex lock.
Yeah. Sure. Yeah.
So once you use real-time tasks, this will breaks. Period. That's you can't. It's broke. Your design is broken as soon as you make something real-time. And correct me if I'm not wrong here, Peter, but I don't even think this whole time slice extension even matters to real-time tasks. Is that right? It's only for SCAD-other, right? I don't think, because except for round robin, maybe.
It will work, but you need to have done your worst case analysis and absolutely ensure that your critical section will fit in the time slice extension. Otherwise, you get to keep the pieces.
Yeah, but I'm saying with if a real-time task, does the time slice extension even work for real-time tasks?
Yeah.
But I thought we had it so that, I thought Thomas was always like, no, we don't, the real-time task could always preempt.
Currently, it does not work for preempt RT kernels.
Oh,
But I think I'm gonna change that and set the default timeout to 0. So it's effectively disabled. But then, so the problem is we need a value. So any value you put in for time slice extension will by necessity compound on your scheduling latency, which is why preempt RT does not have this.
This is where I guess you and I disagree with them.
No, I mean, it is absolutely the same as a preempt disable section in the kernel. There is no difference.
But the whole point, well, I guess that's why I point at preempt RT is to get rid of all those.
You cannot.
Well,
We have
tried.
the spin locks. It's just to minimize them and to make sure that every single one of them is bounded. And that's the thing that makes it a real-time system. So regular Linux has the spin lock, and all the critical sections are not necessarily bounded in time.
I know, but the point I'm saying is if you have this extension, it actually adds to it basically increases the minimum latency by that extension.
No.
Because if the interrupt goes off and you wait, so basically you have a task, I guess because you're on a different CPU. So if it has to be
so on the same CPU, since it is user space, the actual scheduling latency will be the maximum value of this thing and whatever the kernel scheduling latency is with its preempt disable. And as long as this value is less than the inherent latency of the kernel, it's invisible.
Let's see.
I mean, that's how it works. If your interrupt hits while in kernel space in the preempt disabled region, it will need to sit out that preempt disabled region. There's just no way around it. Since we hit user space, we know there is no kernel space, and therefore it's the same. So it's the maximum of this user space extension value and the maximum preempt disable region in the kernel. So for normal kernel builds, we've set it on 5 micros, I think I made it. It's a small value. It's less than most machines. But for preempt RT, if you run it on a good system, that's about where the kernel, where your scheduling latency would be. Suppose your systems will be faster still. Say in 2 years we'll have a 7 gigahertz chip, and who knows, right?
Worrying about light speeds.
Yeah, details. No. The point is that if we ever get a machine where the kernel scheduling latency is less than the 5, this will be a problem. So I want to enable it for preempt RT, but set default to 0, so to have this effectively disabled. And then it becomes the administrator's purview to set the value that matches the system requirements.
Okay.
So now that we have 2 different solutions that basically try to solve the same issue, we can compare them and evaluate them. So first of all, we have, I'm going to show a single lock microbenchmark. So it's a very simple microbenchmark, just to show whether each of them work properly. So here we will show the number of threads on the x-axis, and on the y-axis we have the latency once again. I'm going to use the Futex, the pure blocking lock, as the baseline. Yes, so I said everything in there. We can add the MCS lock. So as you seen earlier, the MCS lock performs better than a pure blocking lock in non-subscription, but in over subscription, it does collapse. Then we have the P1 mutex lock from JLibC, for example, which is worse than the pure blocking lock in that case, because it supports way more things than the mutex lock does.
Sorry, what's the size of your critical section? What does your critical section do here?
The critical section is just writing two cache lines. Two cache lines it's writing things in two cache lines. Yeah, but they are non-dependent writes to like not have any optimizations or anything. So unsurprisingly, the spin lock plus the time class extension, so the very simple solution I presented with the test and set does not work very well because due to cache line contention, the test and set lock does not.
This is 104 CPUs banging the one line.
Yeah, so it's very bad.
So the idea with user space bin locks is that it's fine grained and not intended,
But isn't the pure blocking lock is faster because of convoying, right? It's so slow to wake up that some other thread is doing.
Yeah, exactly. Yeah. It's doing lock stealing all the time. But in the non-oversubscription case, in the oversubscription case, you also have that, but it helps a lot to not have too many threads runnable at the same time. And then we have the solution with the MCS plus the time class extension. So as you can see in this benchmark, and actually this will be, so spoiler alert, this is the same results basically we get in the other benchmarks. So this one performs similarly to MCS, even better than MCS in the non-oversubscribed case, but in the oversubscribed case, it still collapses less than MCS itself, but it still collapses. And when we trace that, we can see that there's actually too much contention on the lock. And so the time class extension happens, but then afterwards, the same thread will try to acquire the lock again, and it will not be granted the time class extension because it gets run too much in the.
Due to the severe contention, your critical sections become longer than the extension time.
No, I think what happens is you grab it more than you enter it too many times.
Yeah, you enter it too many times.
Just says no.
Yeah. You were granted the extension at some point, and then very little time after that, you want to request it again, and you don't get it that time. And so in that case, we can see that there are a lot of critical section preemptions still, even though we have the time class extension enabled. And so if you increase the time of the extension, this will not change anything. So we have the FlexGuard solution here, which performs once again similarly to MCS in the non-oversubscription case. And when we get to oversubscription, it avoids the performance collapse of the other spin locks. And finally, I also combined the two different locks, the FlexGuard solution and the time class extension. And
here's a question about the you had the yield in there too. So if it was granted, you should be yielded. The first time you granted it should have yielded. So it shouldn't.
Yeah, it does yield.
So then why?
Because you cannot ever start a second extension, you shouldn't be able to. If you do, that's the user's failure.
Yeah, there's a yield in after a critical section time class extension. Sorry.
There are many CPUs in this system, and if the tasks are not in the same CPU, the yield is gonna not happen.
What? Oh, the yield? No, the yield. The yield isn't a normal. It's not a sched yield. It's if I'm granted an extension, once you release the lock, you're supposed to say, okay, now let me schedule me out.
Yeah. Every time you have been granted the extension, you must then yield.
Yield after you
if you start another, or if you request another extension, you will not get it, and you will get trouble.
So that's why I'm wondering why you saw that.
Yeah, because you said you were asking for another extension, and
but later on,
something that should ever happen.
No, but after the yield.
Yeah, but you should not be. There shouldn't be. Contention. There shouldn't have contention there.
Yeah, I see what you mean.
So I wonder what happened. Are you sure you had the yield? Maybe it missed the yield.
No. I see the yield on the traces, so it's there.
Well, that's interesting.
But basically, what happens is in traces we can see that the critical section gets preempted again, even though it requested the extension. Yeah, I have to look into that a little bit more.
Oh, you know what it might be? I'm wondering if it's, like you said, once you put in the flex where it would block if if it detects the owner isn't running. So maybe it wasn't the extension that was causing the thing, it was the spinning while.
Another note, so the second waiter, or the second node in your queue log,
Oh,
that one could be preempted while it's.
yeah, you do the, like, it had the code, it did the request and it spinned while waiting for the
But-
thing, so it.
But that's the first waiter.
That's the first waiter.
Another waiter after that, and that's also spinning on its own node. And there's another waiter after that that's also spinning.
Yeah, they are all spinning. Yeah, but they are not.
If they get preempted while they're known first, and then they get promoted to first, you're still up a creek.
Yeah. Yeah, basically here there's still one heuristic, which is the length of the critical section. Is if your critical sections are very short, you probably will can have preemptions of the next wait or next wait.
Yeah, and here you have 104 waiters.
Yeah.
103.
Yeah. Yeah, and so we combine both solutions, and this solution actually is it's performed similarly to FlexGuard, but in that case, it is a little bit more stable at very high subscription levels than the normal FlexGuard. Now, there's one interesting thing is why is FlexGuard outperforming the blocking locks, even though it's supposed to be blocking in that case. So here is a trace that shows on the x-axis you have the benchmark time, and on the y-axis you have the number of runnable threads. So basically, the number of threads that compete for the CPU. Here we are running the same micro benchmark as before with 140 threads, but the machine has only 104 CPUs. So we are in the oversubscribed scenario here. As you can see, MCS and also the MCS plus time series extension have a number of spinning waiters, which is equal to 140 because they never block. So that is way higher than the number of CPUs, and that explains why MCS performs very badly, because there are a lot of preemptions, and it's very likely to preempt the critical section. On the other hand, the pure blocking log, so a pure futex, has a number of runnable threads, which is closer to 0, closer to 1 actually, because there's a critical section that runs. But the next waiter is not running, and so that explains why we can still gain some performance even in our subscription. Because what FlexGuard does is that it achieves a balance between the two. It has a number of spinning waiters, which is higher than 0, so you have a few waiters ready to acquire the lock and enter the critical section right away, but you don't have too many spinning waiters that the CPUs get oversubscribed, and then you get preemptions. So basically, we get kind of uncollapsed spin lock behavior in oversubscription. Yeah, and one interesting thing is you can see the critical sections preemption here and preemptions, and when we switch from spinning to blocking. No, these are some benchmarks, but this is a bit too much. I'm going to show 2 of them, but basically all of them kind of work the same way. So this is LevelDB. This is the re-random benchmark. LevelDB uses peaceful mutex locks, and it uses like 2 locks basically all the time. On that, and that's on the same Intel with the 104 cores machine. And then we have Raytrace, which is another benchmark that uses a few locks from the Parsec benchmark suite, and we run that on an AMD machine with a 512 cores. I don't have any benchmarks on ARM. Sorry, I didn't do that. So in the non-oversubscribed case, so when we have less threads than cores, we can see that the spin lock plus the time series extension it's once again as bad as the test and set lock, but that's expected. The MCS plus the time series extension actually performs worse than MCS in these cases. This is yeah, I don't exactly know why that is, but basically we have this is a bit, the construction is a bit different than the normal MCS lock, so maybe this is the case. But the issue is FlexGuard does use the same construction with the queue and then the first spinner that spins on a global awkward. So FlexGuard should perform the same as the MCS plus timespace extension. So there is an overhead here. And finally, FlexGuard actually outperforms the blocking locks in that case because it is a spin lock. Yeah,
Question about that.
go ahead.
So this is kind of an unintuitive parallel speedup graph because it seems like level DB is incredibly non-scalable. Like you start with throughput of 8 and you don't even get to 16. So less than 2x parallel throughput. Why is it so incredibly non-scalable? And then we're running it up to 250 cores when it only gets a speed up to what, like 2 cores, 3 or 4 cores?
Yeah. Yeah, level DB does not scale very well with the number of cores, basically. It's
So this is kind of worst case scenario.
yeah, basically.
Things, 2 bottlenecks.
Yeah.
Okay.
That's why it's very widely used to compare spin locks, to compare logs basically, but even more spin locks, because it uses, I think it uses 2 logs. There are 2 logs that are very contented, and that's it. So yeah, it's very bad in terms of
It's like a
scalability.
pattern.
Yeah, and so as I mentioned earlier, we can have a oversubscription that's caused not only by the application itself, but sometimes by other concurrent workloads. And so we wanted to see what happens with this. And so I can show you here 2 different benchmarks where we have concurrent workloads working on the same machine as the application. So the application has a fixed number of benchmark threads. You can see them at the bottom. Basically, it's half of the number of cores. And then we vary a number of concurrent threads on the same machine to be in the oversubscribed case in both of these graphs. So in all of these oversubscribed cases, the MCS plus the timespace extension lock does not avoid the performance collapse. So once again, this is probably what we were discussing before. So the next waiters can be preempted, can still be preempted, and there are some issues with the critical section still getting preempted. So there are some ways to improve this probably. We need to do more about that. And then the FlexGuard solution outperforms the blocking lock. So once again, this is due to the same thing I showed you earlier, where we can see the number of runnable threads is higher than the Qtex lock. And so the lock can be transitioned from one thread to another quickly. Now, there is one case where the FlexGuard plus timespace extension solution works better. It's not only one case, but here I'm showing one case, and this happens in some benchmarks. The issue is that FlexGuard is limited by its ability to put threads to sleep. Basically, if you have all of the waiters are currently spinning, then you can switch them to blocking, and then you get a machine with a blocking lock, basically. But if you have a number of waiters which is quite low compared to the number of threads on the machine, then the lock order may not get rescheduled quickly enough, and then it may not increase performance that much. And so that's one case we have here using a database index. It's benchmarked by some researchers. They made a benchmark that shows how DB indexes use locks basically. And on the AMD machine, for example, we see that it does not have enough waiters to have the same performance as the FlexGuard plus timespace extension solution. And here, this timespace extension can still help because it does not need to switch anyone to blocking, basically. So that's why it's the best solution here. So yeah, the combination of both solutions is actually the most consistent one to ensure good performance in all of our benchmarks and everything we tested. So now to conclude, so FlexGuard allows the use of a user space spin lock even in oversubscription. And as I said, we get spin lock behavior without the collapse in oversubscription. So this could be adopted in more synchronization primitives. The detection of the critical section preemptions could be done for rewrite logs, condition variables. Barriers are complicated to know who's the next one, but this is all something that could be done. And then we could also detect vCPU preemptions to detect when a lock is taken by a thread that is currently running on a non-running vCPU, basically. So yeah, you can have the code here and more information. On the timespace extension side, so it reduces the critical section preemptions, but it does not prevent the performance collapse, at least not with the logs we tested. because under high contention, many critical sections are still preempted. Some specific lock designs tailored to this time series extension solution may help, but I try to implement it for many locks, many state-of-the-art locks. And it actually does the same thing as the MCS plus time series extension solution. So I still haven't found a good lock to have very good performance using this time series extension. And fine.
Isn't this why Linus also said you need to fix the locking, not the lock?
Yeah, probably.
Yeah.
This is in all of these benchmarks, the locks are very, very contented, and they probably should not be very, very contented like that if they are either spin locks. So yeah, I agree. But level DB has been like that for, I don't know, like 15 years or something like that, and it has not been fixed and still widely used. So
bad code will always exist.
Well, from what I've told is that, yeah, the locking is the issues there, but
if they don't care about the performance.
no, they do care about performance. So that's why, well, they found that the user space is better than what we give them. The user space bin locks is better. So I mean, why, if we improve the user space bin locks, I mean, if there's a solution that actually makes things better.
Yeah, and if we combine the two solutions, it is actually the best solution it works with a limited number of waiters. So if you have any more questions, these are some benchmarks if you want to look at them. Yeah.
And so on real workloads, so the implementation was you replace the mutex implementation with this one.
Yeah.
Does it hold the lifetime extension on the user level critical section, or you just use it in the mutex implementation? Is the critical section covered by the lifetime extension?
Yeah, it is covered. Yeah.
It works because I mean, isn't there like a constraint that you cannot do syscalls, for example, during a lifetime extension in the kernel?
Sure, but why would you need I didn't get that. Why would you need a syscall during the critical section?
So you don't control the critical section, right? It could be anything.
Oh yeah.
It could be as soon as you call malloc, there could be a syscall.
Yeah, sure. But all of these benchmarks don't have syscalls in the.
None of level DB during any critical section never does another.
No, because I have a benchmark that tried that, and it does crash if there's a syscall in the.
Maybe just rare, so it's possible to do that.
Yeah.
Did you measure fairness in any way?
Yeah. So
imagine that this could have a bistable behavior where some threads just always stuck in the blocking phase, and some are always spinning, and so they get starved.
You mean for the time series extension?
In general, for the flex behavior.
Yeah. So for FlexGuard, the along your application it's kind of the same as an MCS lock. But when you do switch between spinning and blocking, you do have a fairness issue here because we have two different queues. Actually, we have the MCS queue and the Futex queue, and so the threads can be in another order basically when they switch from one queue to the other. So yeah, you do have a fairness issue here. What was your second question? Sorry.
This is fixable, by the way.
Yeah.
So if you have the eBPF thing set the MSB to indicate that there are Futex waiters, and then have the spinners stop spinning so that they'll also queue, then you get your fairness back once you get a FlexGuard blocking.
Okay, I will look at this. Did you have?
You answered the question.
Okay. Thank you.
We've fixed a whole bunch of